come to another topic in the blast furnace, and that is physico-chemical phenomena in blast furnace. And this is sort of a heart of the blast furnace in one way we would say, because all the chemical reaction which is occurring, the thermodynamics behind it, how it can be improved, what are the limitation of it, this actually we would be discussing in this topic. So, from thermodynamics, reaction kinetics, and in fact knowing the limitation of the furnace, from this viewpoint this topic is very important. So, we will go to various systems in the blast furnace which are of important to us. The first one is the iron and oxygen system. So, iron and oxygen system, when we talk about it, first one comes to in our mind is about the iron ore, which is hematite, and which is nothing like Fe2O3. So, the common structure of this is hexagonal in nature, which mostly for alpha F2O3, and it decomposes at 1470 degrees Celsius into magnetite and oxygen, and oxygen content in this is about 30%. I have shown one calculation how do you determine this oxygen content. So, 2 mole of iron, 3 mole of oxygen. So, that gives you the molecular weight of Fe2O3 160, and therefore, oxygen would be total we have 48 divided by 160, and in the percentage term multiply by 100, that gives you the 30% oxygen in hematite. Similarly, we can calculate for other oxides. So, we will not show these calculation and we will just refer the percentage, but one can do it. So, magnetite it is cubic in structure and contain about 27.64% oxygen. It melts at 1870 degree Kelvin. When hematite transforms to magnetite, the hexagonal structure changes to cubic structure, and which causes volume expansion and increase the porosity. And this is the thing which lead to a little bit expansion of the ore in the blast furnace. I think in the first few lectures we talked about swelling and other thing, and this causes one of that one. It is not. So, this is one region. Now, we have bustite FeO. It is unstable below 843 degree Kelvin, that is 573 degrees Celsius. So, it does not occur in the nature. So, one should know FeO is not a naturally occurring compound because it is unstable. On slow cooling, it decomposes as follows. So, it gives actually magnetite and iron. So, it contains about 23.2% oxygen, and composition corresponds to this ratio. So, this is a stoichiometry not right in the form of FeO, because oxygen ion content differ, but in terms of convenience way we just write FeO, and that tells you the heat of formation and the composition of all these three important oxide which are part of the blast furnace. So, molecular weight and the ion content in it, and the oxygen content and a heat of formation at various temperature. So, there are 4 important systems in the blast furnace to understand its chemistry, reaction, chemical equilibrium, etc., which will ultimately give an idea about improving its efficiency, advantage, limitation, etc. So, this system are iron oxide system, we just saw that carbon oxygen, iron carbon oxygen and iron hydrogen oxygen. These systems will be discussed now one by one in the coming slides, and application of these systems towards the blast furnace application would be discussed. So, CO system, carbon react with the oxygen as follows. So, 1 mole of oxygen combined with carbon, 1 mole of carbon gives you the 1 mole of CO, and the change in free energy is given from this expression. The standard one, T is the temperature in degree Kelvin, joule per mole, and the another reaction which forms CO2 when oxygen combined with the carbon, it is given represented by reaction number 2, and the free energy expression is given by this, again T is in degree Kelvin, joule per mole. So, you can see both are exothermic in nature, and this when CO form in this, it can further react with oxygen from CO2, and free energy is given again for this reaction. Similarly, CO2 which is forming here can react with carbon, can give you CO 2CO. These two reactions or even this reaction is possible when reactants are more in quantity. So, whatever is formed they again react, and because especially at higher temperature CO is stable. So, it is again from the CO, and when CO2 is converting reacting with carbon and forming CO, that is usually an endothermic reaction. So, for pure carbon that activity is taken as 1, and activities of gaseous species are equal to their respective partial pressure, which I am sure all of you might be aware of these activities, free energy and other thing from your thermodynamics course or reaction kinetics course. So, we are not going to tell about these terms, and we expect that you would be knowing about it. So, that is why this and this can be converted into partial pressure. So, therefore, at equilibrium if we look at the this reaction number 2 that we have put, the free energy can be written RT log K2, and this K is nothing, it is a equilibrium constant for the particular reaction. So, we are considering this reaction, and you can easily write the equilibrium constant K equal to PCO2 divided by PO2 and SCS. So, that is activity of carbon, and activity of carbon, as we said we are considering is a pure carbon, it has been assumed 1. So, the equilibrium constant boils down to this expression PCO2 divided by PO2 for this reaction. So, and we substitute that equilibrium constant over here, and we know the then the free energy, this is for the other reaction, that the first one where the half mole is converted into CO. So, that gives for the free energy expression in terms of partial pressure. Similarly, for other we can put it for the number 4. For this we can write again 2 moles of CO are forming. So, the equilibrium constant is this, and now this can be written in terms of mole fraction, and we are assuming pure system where CO and CO2 only are there. So, total pressure would be 1 atmosphere. So, these thing one can interchange, can write in mole fraction, volume fraction, partial pressure and other way, and I hope you read, those who are taking this course, they are familiar with these terms. So, from the above expression, the value of equilibrium constant K can be calculated for each reaction. So, reaction 1, 2 and 3 are exothermic in nature, as we said before, because they is having a negative free energy, while reaction 4 is endothermic reaction. Reaction 1 and 2 occur near the TUA, where the value of K1 and K2 is very high at the TUA temperature of the order of 10 to the power 6. So, this value you can calculate for this one at TUA temperature, taking about 1900 2000 degrees Celsius, and free energy you already know. So, log K, you can get it this, you put it log K, and delta G expression you already know for these reactions, put it that, and you can R it is universal gas constant, T the temperature. So, temperature suppose is 2000 degrees Celsius at the TUA level or 1900, one can calculate the equilibrium constant value. So, equilibrium constant value at that comes very high of the order of 6, and in fact, another one is of the order of 9. So, indicating that partial pressure of oxygen is negligible. So, naturally the partial pressure of this, if this is of the order of 10 to the power 6, partial pressure of oxygen would be very low, and which indicate that all the carbon converted into CO and CO2 at the TUA level. So, reaction 4 is very important reaction, what we call it, it is a Woodard reaction in metallurgy in iron making, and you also call it gasification reaction, even solution loss reaction. There are various way of telling about that reaction number 4. So, Woodard reaction, solution loss reaction, gasification reaction, because carbon is losing. So, if in the reverse reaction is known as, so if it goes in a reverse direction, so what is happening, carbon is coming out from the CO. So, it is called the carbon deposition reaction, and CO2 is forming, and that is when it is going in the reverse direction, depending on the temperature and the kinetics of this. So, reverse direction reaction actually is exothermic in nature, though you can see it is in endothermic in nature in the forward direction, but in reverse direction it is in exothermic in nature, this reaction. So, reaction 1, 2 and 4 are dependent on temperature and pressure, as we have seen with the free energy relation with respect to free energy expression. So, these can be plotted in graphical form. So, figure below shows the Woodard reaction at various temperature and pressure. So, this is the Woodard reaction, carbon gasification reaction, and one can see plotted temperature versus CO plus CO2 ratio. So, this actually tells how much CO is being utilized, and as you can see below 600 this becomes quite sluggish, or 500 or below 500, 400. In fact, this reaction it's almost ceases in the reverse direction. Though at 1000 degree Celsius you can see it fully converted into CO, and CO2 is no more is there really. And but in this one the reverse is occurring, but after this is almost ceases the reaction. And as the but the most unstable region actually is this, where this between I would say 600 to 800, where this is changing rapidly. This is the region which is very unstable, and you can see the slope of the curve. So it is seen that CO percentage decreases with increased pressure. So with the increased pressure, CO percentage decreases. At the same temperature we will take it, but it increases with temperature. So with the temperature CO percentage is increasing, and the maximum instability of CO lies between the temperature range of 600 to 800 degrees Celsius. And our in the blast furnace mostly reaction is occurring after 800 to 1000, where we have a chemical or thermal reserve zone. So that is where it is reaction in the blast furnace occurs, a reduction reaction. Now the decomposition of CO is a very slow process. After 400 degrees Celsius, as we have said, is almost ceases after 400. So decomposition is very slow. In the presence of catalyst which provides nucleation site, it is accelerated as shown in this figure, and this is with respect to presence of iron. So iron becomes as a catalyst, and so this reaction is accelerated. So above 1123 Kelvin, 900 degrees C, the reaction virtually ceases, as we mentioned in this one. Above 900 degrees C, this is almost over, this reaction does not occur in that one. So you can see in the presence of magnetite, carbon deposit is maximum. So when hematite in the stake region at the top is reducing to magnetite, that time temperature is also favorable in the stake region, carbon deposition occurs. Magnetite actually accelerate that, and that is the maximum you are getting it at 500. And hematite of course does a bit, and bushite is the lowest one, and iron is in the middle. So magnetite is the one which will favor or accelerate this reaction, and that is in the stake region, and at the top where the preheating zone and this thing which we discussed, temperature goes from up to 600-700. So that is the region when this carbon get deposited. It has many disadvantages, besides some advantage, but mostly disadvantage. So deposition of carbon in blast furnace reduces the stake diameter. So it deposits, and so diameter of the stake is decreased in the terms of more mass has been added. So that causes breakdown of charge material, also retards burden descents, and finally leads to the hanging of the furnace. So these are the major problem which occur due to the deposition of carbon, and one has to be careful and design in a way the blast furnace reaction or the temperature zone that it should be minimized. One cannot completely get rid of this, but it should be minimized. Now we come to the third system, it is iron, carbon and oxygen system. So, and this is the one which is quite prevalent in the blast furnace. So, in the blast furnace CO is produced near the TUR region, which ascends and reduces the oxides of iron. Following important reaction takes place. So, obviously, the first one we are going from the top. As soon as you charge the ore, which is mostly hematite, it reduces with carbon monoxide, CO2 magnetite, CO2. You can see this is an exothermic reaction. Then magnetite, when we further go down, magnetite convert into boostite, and this is an endothermic reaction from the free energy. And then this FeO converts into iron, this is slightly exothermic reaction, but you know this FeO which has formed must be more than 570 degrees Celsius the temperature, otherwise if it is formed below that temperature, then it will dissociate as we discussed before, because it is not stable, and it will form iron and CO2. In fact, some of the iron fissure has been found in the upper zone of the blast furnace. So, this also reaction sometime occurs below 843 Kelvin. So, reaction 5, 6 and 7 are called indirect reduction reaction. So, you can see they are getting indirectly reduced by CO. So, these three reactions are called indirect reduction, and you must have heard about the direct reduction, but as such really there is no direct reduction takes place via. So, direct reduction takes place via gas phase only and not by solid carbon, except where molten material is directly in contact with solid carbon, which is mostly in the Bosch and the hearth region. So, by that time most of the FeO is already reduced. However, that is why this direct reduction, the way you represent it, actually it goes via gaseous phase. So, FeO plus CO, iron plus CO2, CO2 plus C gives you 2 CO. So, gasification of carbon is occurring, and when you add both of them, this gives you this reaction, which what you call like the direct reduction. Essentially, it is not the carbon directly reducing it, it is via gaseous phase it is getting reduced. Overall reaction is known as this one, which you call it a direct reduction. So, the overall free energy for this, and you can see it is highly endothermic reaction, very high endothermic reaction. So, it needs quite a lot heat to get that. So, from equilibrium constant value of reaction 5, the ratio of CO2 to CO is almost negligible, which means reaction almost goes with 100% proceed in the right direction. So, this is the reaction 5, this hematite. So, this reaction, the ratio of CO2 to CO is almost 100%, which means the reaction proceeding in the right direction, and almost 100% get completed. Note the other reactions. So, figure on the next slide you will show the stability phases of iron and its oxide in presence of CO-CO2 mixture. So, the upward, so this is the Fe, C and O system, where you are having so this is the line which you have seen for the CO system, carbon and oxygen. So, it has been superimposed in the on the FeCO system, just to say how the reduction will take place. So, essentially FeCO system is this one, where these lines are there. So, above this line iron is stable, boostite is in between, and this is all magnetite region, and this is all iron. So, you can see at this point 570 degrees Celsius which we talked, that is where the FeO, which is here boostite, is no longer exist below that and getting directly reduced to magnetite and iron at this. So, this is invariant point of that, because oxygen content in boostite changes, because stoichiometry is not 1 mole of Fe and 1 mole of oxygen changes. That is how these other lines are given here. Now, in the curve, so as the upward slope of the curve shows the reaction are exothermic. So, you remember this is the upward one, you know these reaction are with exothermic, and we found one is endothermic, actually is the downward one. So, the equilibrium concentration of CO for Fe3O4 FeO is almost 20% at 1173 degree Kelvin, and from so this is a Fe3O4 FeO content, and usually we talk around 900 degrees Celsius or so. So, at that if you will see it is about 20%, coming to about 20% CO, and that is where what the equilibrium concentration of CO is about 20%. And usually the extent of utilization of CO is expressed in terms of the efficiency of the carbon which says. So, this is the efficiency of utilization of CO equal to percentage of CO2 divided by the total percentage of CO plus CO2. The ratio of this tells you about the percentage of utilization of CO for the particular reaction. So, with respect to that what we discussed just now, it would be for magnetite FeO 20% CO utilization, it would be 80% efficiency of CO for this reaction. Similarly, for others one can calculate, and this this is the CO carbon gasification line which tells where this reaction will occur and how it is going to reduce, or to reduce let us say the FeO, what sort of how much CO you need it to reduce at a particular temperature a particular oxide.